Hi everyone. Today I'm going to talk to you about sending encrypted data and teleporting quantum particles using one weird trick. So a lot of the stuff in this talk is based on this book called Picturing Quantum Processes, written by Bob Kuka and me. You can find it in various places on the internet, or you can ask a librarian if you like things to be free. Okay, so let's get to the question. So you know when you click one of these clickbait things, normally you have to scroll all the way to the bottom to figure out what the trick is. Well, unlike those pages, I'm going to tell you what the trick is right here at the beginning. The trick is string theory. But I don't actually mean this kind of string theory. I mean this kind of string theory. This theory of strings, actually, how strings work. And what we'll see by the end of this talk is that the weird trick is that if I have this kind of zigzag piece of string, I can just pull it straight. Okay, so before we get there, I'll tell you a little bit about quantum theory. What is quantum theory? Well, typical quantum systems, so quantum theory is the theory of very small particles. Typical quantum systems are photons and electrons. But lots of the basic rules of quantum theory work the same no matter what the system is. So you actually don't really need to know any physics to understand what some of the basic principles of quantum theory are. So we'll focus on a more hypothetical alternative quantum system. This is Dave. Dave is a dodo. Dave is a quantum dodo. So Dave's state is given by the simplest quantum system there is, a qubit. So what's a qubit? Well, before I explain to you what a qubit is, I'll say a little bit about what a bit is. Well, rather than telling you what a bit is, I can tell you what it does. So a bit admits two different states, 0 and 1, and it's definitely in one of those states, right? It's the light switch is off or on, right? So off is 0, on is 1. And it can be updated any way we like. So for instance, if I look at a bit and I see that it's 0, I can change it to 1. And if I see that it's 1, I can change it to 0. Okay, so this is called applying a NOT gate to a bit, right? Transforming 0 to 1 and 1 to 0. But of course I can do other stuff to a bit. For instance, I can ignore what the bit is, and if it was 0 or 1, I could just send it to 0 in either case, right? So this is kind of like erasing that bit. Perfectly fine. And bits can be read freely, anytime, no problem, right? So it doesn't cause any trouble if I just look at the bit and see what the bit is. Okay, so qubits are a bit different, but they're a kind of a quantum analog to bits. So rather than admitting just two different states, they admit an entire sphere of states, which is quite an interesting space to work with. But they can only be updated without destroying them by doing rotations of the sphere. Okay, so I can think about, the state of my bit is my qubit is some point on the surface of this sphere, and I can change it by rotating the whole sphere to move it somewhere else. Okay, and crucially, qubits can only be accessed by special processes called quantum measurements. And doing a measurement actually destroys the qubit, or at least it changes its state in a very drastic way. Okay, so let's see how this works. Rather than focusing on some abstract mathematical sphere, we'll take a sphere that we all recognize. So here's the Earth. And now, as a matter of convention, I'm going to pick two different points on Earth that represent the bit values of 0 and 1. This is just a convention, and to make things simple, I'll choose the North Pole and the South Pole. Okay? Now suppose Dave is in some other state, so he's at some other place on the surface of this sphere. Let's say here. Okay, and we want to determine where Dave is. Well, since Dave is a quantum dodo, we can't just ask him where he is. Well, we can't simply ask him where he is. So here are the rules. The rules are that we're only allowed to ask whether Dave lives at a specific location on Earth or the opposite location. And Dave will always answer correctly to the best of his ability. But it's correct in kind of a weird way, because we asked him that if he's at one of two possible points, but as soon as he answers, he actually will be at the answer that he said. Okay? So that's a little strange. Let's go through an example here. Okay, so suppose I ask him, are you in New Zealand or Old Zealand? Right, so what's New Zealand? We all know where that is. That's Middle Earth. Right? Old Zealand, or Zeeland, is a province in the Netherlands, which is actually pretty close to where Dave is in this picture. Okay? So now I ask him, Dave, are you in New Zealand or Old Zealand? And Dave, since he's a truthful dodo, says Zeeland. And actually he doesn't go anywhere because what he said was correct. But now suppose I ask Dave, are you at the North Pole or the South Pole? Well, he's at neither of those places. But since he's a quantum dodo, he has to give an answer when I ask him this question. So suppose he says South Pole. Well, if he says South Pole, as soon as he answers, then he goes to the South Pole. So as soon as I measure my qubit and I get outcome 1, it is in that 1 point, so the South Pole of the sphere. Suppose he says North Pole. Well, if he says North Pole, then he goes to the North Pole. And then he gets eaten by a polar bear. Okay, so that's basically an overview of well, that's not everything you need to know about qubits, but that'll be enough to get us going. Okay, so I'm going to take a step back from giving you that very rich introduction to quantum theory and talk about something that's a bit more general than quantum theory, and I'll talk to you about process theories. So a process theory is something that's made of processes. Okay, so what do I mean by a process? Well, a process is something that has some inputs and some outputs. Okay, and that's about it. That's about all I mean by a process. So here we have some inputs going in the bottom of some process called P, and then something happens, and then some outputs. Okay, so that's very abstract, very general. So let's look at something that you've probably seen before. Okay, something like a mathematical function is a process. Okay, so here's a function, f, which takes two inputs, x and y, and it gives some output which is computed from its inputs. So maybe by squaring x and adding y to it. Right, so rather than writing this as a formula like you're used to, I'll just write this as a box. So this box is labeled f, that's what process it is, and it has two inputs, which are labeled num, so that's the type of thing that's coming in those input wires is a number. And then one output num, so there's a wire with the type number coming out the top. Okay, and now I can imagine this thing as like a little machine that I can plug numbers into the bottom of, and numbers sort of spit out the top. So if I, for example, plug a 5 and a 1 into the bottom of this box F, then 26, so 5 squared is 25 plus 1 equals 26, pops out the top. Okay, so that's a process, a certain kind of process. And processes can do anything, including nothing. So in any process theory, there's a special do-nothing process. So in this theory of functions, it's this function. So f of x equals x. So what does this function do? Well, it does nothing. If I put 5 in the bottom, then 5 comes out the top. If I put 17 in the bottom, 17 comes out the top, etc. Okay, so processes can also be anything. So not just math. There's a lot more processes than just mathematical functions. So you can imagine like a computer program as a process. So here's a program called Quicksort, which takes in a list and it puts out a list of sorted elements of that list. A physical device could be a process, right? So binoculars have two lenses which let light in and then two lenses that let light out. ideally magnified or maybe shrunk if you're holding them backwards. Cooking is a process. So here's a very special recipe, right? So here I've got eggs and bacon coming in the bottom and breakfast coming out the top. It's a perfectly good process. And baby is a process. And as we all know, a baby is a process which converts food and love into noise and poo. Right? So processes can be anything. It makes sense to define a process for just about anything. But not all processes make sense to plug together. So for example, if I take baby and I try to connect it up with quicksort in this particular way, unclear what the output of quicksort will be in this situation. Now, a family of processes which do make sense together is called a process theory. So some examples of process theories are functions, like what we've seen so far, mathematical functions. You could also imagine having logic as a process theory, where maybe your deductions in your logic are processes. Electrical circuits, here your wires really are wires and your boxes are little transistors or resistors and so on. That's a process theory. Computer programs, maybe in some particular programming language, quantum theory, and so on. So there's lots and lots of process theories out there. And right at the beginning, I need to tell you what process theory I'm working in when I'm doing things in this particular style. Okay, so let's look at an example of a process theory. And I really like this one because it has a lot of quantum-like properties, but it's also very easy to understand. So this process theory is called the theory of relations. Or if you would like another way to think about them, they're like unreliable functions. Okay, so they're a generalization of functions like we talked about before, but they're unreliable. So what's that mean? Well, here's a normal function from a bit to a bit, okay? And a function is just something which sends every particular value in its input set to some value in its output set. And importantly, it sends every one value to only one other value. Okay, so for instance, this thing, the NOT gate, or the NOT function, sends the bit 0 to the bit 1, and it sends the bit 1 to the bit 0. Okay, but since we're allowed to have unreliable functions or relations, we can define this thing, the WHAT gate, which sends one value to more than one value. Okay, so it sends 0 to 1, and it sends 1 to 0, but it also sends 1 to 1. Okay, what? This is a perfectly good relation. And what this means is that I have a device or a map, and I'm not sure exactly what it's doing. Okay, so maybe I've got some sort of box and it's a little bit defective, or there's a little demon in there who's actually, when I input a 0 into this box, it works just fine. It puts out a 1. But when I put in a 1, sometimes it works fine and it gives me a 0, and sometimes it decides to mess with me and give me a 1. Or you could think that, there's some randomness or something, like I'm actually, when I put in 1, I flip a coin and decide to give me 1 or 0. These are all perfectly good interpretations for what this WHAT gate is doing. Okay? And these are quite useful objects for modeling different kinds of situations. Okay, so relations can be plugged together. So as soon as we have these boxes and wires, we want to know what happens when we plug wires together. And what happens with relations is we can plug them together just by tracing the paths. Okay, so in this case, I have two relations, R and S. And this relation R, well, first it relates A1 to B2, and then it relates B2 to C1 and C2. Okay, so when I plug R with S, I get this relation, and what it does is it relates A1 to C1, and it relates A1 to C2, and so on. Okay, so you see all I've done is I've drawn this picture like so. And I've traced all the way from the left to the right here. And if there is a path, when I trace this over it, it shows up in my new relation, which arises when I plug R and S together. Okay, so this is how I plug relations together to get other relations. All right. Okay, so the last thing I need to tell you kind of formally about relations is what happens when there's more wires. So a box can have lots of wires in and lots of wires out. And for relations, this just means that it relates lists of the things on the wires to lists of the things on the output wires. So lists of things on the inputs to lists of things on the outputs. Right? So here I have a relation R with 3 wires in, each labeled bit, and 2 wires out, each labeled bit. This means it relates lists of 3 bits to lists of 2 bits. Okay, so here's all of the lists of 3 bits. So 0, 0, 0, 0, 0, 1, so on, so on, so on. There's 8 of these different possibilities for 3 bits. And it relates them to all the possible lists of 2 bits. Okay? So that's what more wires means. It means that rather than just individual items like bits, I'm relating lists of items. Okay, so here's kind of an interesting question. How many lists of 0 things are there? I mean, you might think that there's 0 such lists, but actually there's exactly 1 list with 0 things in it. And I could write it as like a kind of list with nothing in it. Okay, so I'm writing it just as a pair of parentheses here, which means like I've made a list of 0 things. Okay, so why am I talking about no wires? That doesn't sound very interesting. Well, processes with no input wires are called states. Okay, so this is like I have some piece of memory in my computer and I set it to something. Okay, that's what a state does. So I don't care what that memory was up to before, but I'm just going to set it to something. Okay, so some examples of a state for a single bit. So now I have no wires in and I have 1 wire, which is a bit wire coming out. Well, this should be a relation from this empty list to a single bit. Okay, and I have a couple of states that you might expect. So here's the 0 state. That's like I have a bit and it's 0. I have the 1 state, which is I have a bit and it's 1. But since these are relations, since they're unreliable, I can also have the I don't know bit state. Okay, so this means I have a bit, but I actually don't know what it is. Okay, so maybe someone else gave me this bit and they didn't tell me what it was. Okay, so these are the 3 possible states I could have for a single bit. So if I have 2 bits, now interestingly I can have separated states, so I can have states where I have a state of my left bit and a state of my right bit, and I just sort of put them together. Okay, so if I have like this state, 0, 1, well, this means I have 2 bits, and the state of those 2 bits is this list 0, 1. I could have this kind of separated state. Okay, so here I have a bit which is 0, and I have a bit which is I don't know. Okay, so here maybe my second bit, it came from somebody else and they didn't tell me what it was. Well, now I know that overall my state is either I have 2 bits which are in state 0, 0, or I have 2 bits which are in state 0, 1. Okay, so this is a perfectly good state for this relations theory. But I can also have states which are not separable. Okay, and these states are called correlated. So suppose I have this state, which I call the twin state. So here I have 2 bits, and I don't know exactly what they are, but I know that they are equal to each other. Okay, so now I have 2 bits, and it's either the case that those bits are 0, 0, or those bits are 1, 1. Okay, so this is not a state of just one bit put together with the state of another bit. This is a kind of a relationship between two bits, which I can think of as a particular state, the spooky twin state. Okay, and for reasons that should become clear, I'm going to write this as a kind of a cup-shaped piece of wire. Okay? Just like states are processes with no input wires, effects are processes with no output wires. Okay, so this is possibly a little bit more subtle than a state, but the way you should think about an effect is it's like an answer to a question. Like, if I ask the question, what is this bit, then there's at least two possible answers. Well, let's say two possible answers. The bit is 0 or the bit is 1. Okay, so these effects correspond to having observed the bit and getting that answer. Okay, but since we're working in relations, there's also a third answer, which is this kind of yes and no, or I don't know answer. Okay, so this corresponds to maybe my measurement device broke, or someone else did the measurement, they didn't tell me what they got, something like that. Okay, so sets of effects together, or let's say questions that I could ask about my state, are called measurements. Okay, so there's two possible measurements I could do for one bit. There's this conclusive measurement where I just look at the bit and I see whether it's 0 or 1. And there's an inconclusive measurement where I either just throw the bit away or I'm not able to measure it somehow. The information I get out of it is nothing. I don't know if it's 0 or 1. Okay, so that's not that interesting. But for 2 bits, just like for states, we could get correlated measurements. We could get correlated effects. So an example of an uncorrelated or a separated measurement is something like this, where I'm just measuring each of my bits and I can get one of 4 possible outcomes. 0, 0, 0, 1, 1, 0, or 1, 1. An example of a correlated measurement, so a kind of question I could ask about a pair of bits, is are these bits equal to each other? And then there's 2 possible outcomes, 2 possible effects. Either they're equal or they're not equal. Okay, and something that's actually going to prove quite useful is if we express these 2 effects as either our upside down twin state. Okay, so this is like the twin, and I've taken it and I've flipped it around to make it a cap rather than a cup. Or the cap, and I just put a NOT gate on one of those bits. Okay, so if I flip one of the bits and I ask if they're equal, that's the same as asking if they're not equal. Okay, so let's get down to business here and do some actual calculations. Let's compute this zigzag piece of wire in the process theory of relations. Okay, so first our cup was this twin state. Okay, and that's what a cup would be like by itself. Now let's put an extra bit in the mix. So here I've put a bit as my input. Okay, so here's the picture I'm looking at. Here I have one input bit, and I have 3 output bits. 1, 2, 3. Okay, and what do? I just take my input bit and I send it straight through. And my other 2 bits I put into a cup state. Okay, or a twin state. So what is this relation? Well, if I have 0, one of 2 possible things can happen. Either 0 goes through and it gets paired up with 0, 0. Okay, so that's the other 2 bits are equal and they're both 0. Or 0 gets paired up with 1, 1. So here the other 2 bits are equal and they're both equal to 1. Okay, so that's the 0 input of this little picture here. The 1 input does this very similar thing. It's just that I have a 1 in this place now. So 1 goes to 1, 0, 0, or 1 goes to 1, 1, 1. Okay, so if I take this little piece of picture and I plug it in with that little piece of picture, well, now what happens is, in the case that the first two bits are equal, I'm going to send the third bit through. Okay, and then otherwise I'm not going to send the thing anywhere. All right, so let's see that up here. Well, 0, 0 are equal, so I'm going to send that third bit through, and it goes to 0. 0, 0 are equal. I'll send the third bit through and goes to 1. 1 and 1 are equal, so I'll send the third bit through, it goes to 0. 1 and 1 are equal, so I'll send that bit through and it goes to 1. Okay, and now if you remember how to compose these relations, I do it by tracing paths from the left all the way to the right. Okay, so if I do trace that path, let's see, I have one path which goes from 0 all the way to 0. And I have one path which goes from 1 all the way to 1. And I have no other continuous paths totally crossing this thing. Okay, so the composition of these two little pieces of picture is this. Okay, 0 goes to 0, 1 goes to 1. And this is just the do-nothing process, right? I've taken my bit and I've done nothing to it. Okay, so what did we show? Well, we showed that this zigzag piece of wire is actually equal to doing nothing, which is exactly what this little cartoon man was trying to show us right at the beginning. Okay, so that was the spoiler explained, well, sort of explained, but what you're probably asking is, what does this have to do with crypto? You know, I was saying that you could send encrypted messages and teleport quantum states, but all I'm really told you so far is how to yank pieces of wire from bent wires to straight wires. Okay, but actually we don't have to do much or really any more math at this point. I just need to explain to you a very simple way that you can encrypt stuff. So here's encrypting stuff 101. So suppose Alex and Bob, so me and my co-author Bob, each have an envelope with the same random bits sealed inside. Okay, and this bit I'm going to call a key bit. This is like a cryptographic key. Suppose we each have a random bit and it's the same bit. Okay, and I want to send another secret bit to Bob. Okay, so I want to take my bit and I want to encrypt it and send it to Bob. Well, how do I do this? Well, I open my envelope and I look at the bit that's inside and I look at my bit and I'm going to tell Bob if these are the same. Okay, and so I'll just tell him yes or no. They're the same or they're not the same. Okay? Bob opens his envelope, and if I told him that the bits were the same, Bob knows that he actually has my secret bit, okay? Because my bit was the same as the bit in the envelope, and the bit in my envelope was the same as the bit in Bob's envelope. Cool. In that case, he has my bit. Otherwise, Bob flips the bit, okay? So in this case, my bit was different from the bit in the envelope, which is the same as the bit in Bob's envelope. So if he flips his bit, he'll get mine. Okay? Were you able to follow that? Well, if you weren't, let's draw some pictures. Okay, so first of all, let's talk about what these two shared random bits are in the two envelopes. Well, these things are exactly the twin state. Okay, so these bits are sealed in an envelope. I don't know what they are, they're random. But what I do know is that they're the same. My bit in the envelope is the same as Bob's bit in the envelope. So these bits are either in the state 0, 0 or 1, 1. Okay, and now when I open the envelope and check whether it's the same as my secret bit or not, I'm performing this measurement. I'm checking whether they're the same, which looks like a cap, or I'm checking whether they're different, which looks like doing a not to my bit and then doing the cap. Okay, so if we put it all together, this protocol that I explained, of encrypting a message and sending it to Bob looks like this. Okay, so here's my secret bit down here. Here's our shared key bits, which now look like the twin state, the cup state. And here's my measurement of checking whether they're the same. Okay, and then this question mark can either be do nothing, which means they're the same, or it can be a not. And then Bob's fix is the same as I see down here. Okay? And it works. Okay, so there's two cases to look at. In the first case, I open the envelope and I see that my bit's the same as Bob's bit. In that case, Bob doesn't have to do anything. We're done. Okay, so can we see that Bob gets my bit? Well, yes, we just yank the wire and Bob gets my bit. No problem. Gotcha. In the other case, I'll open the envelope and I'll see that the bits are different. Okay, so that corresponds to this particular effect happening. And then I'll tell Bob, hey, they were different. So what Bob does is he flips his bit. Okay, so now what happens? Well, we still have this zigzag piece of wire here. Right, we still have this zigzag here. We can still yank the wire. And then we have a pair of NOT gates here, and it's a double negative. So if I not 0, I get 0. If I not 1, I get 1. Okay, so these things cancel out. And Bob gets my bit. Gotcha. Okay, so it works. And the interesting thing about this is I never told Bob, what my bit was. I only told him whether it was the same as this secret bit that we shared. So if anybody's listening in, they don't get to know my bit. Only Bob knows my bit at the end of this. This is called one-time pad cryptography. Okay, so let's talk about quantum teleportation. So the cool thing about explaining crypto in the way that we did is now quantum teleportation works in the exact same way. All we have to do is sort of flip a little switch and change the process theory. I know, right? Okay, so what does that mean? Well, that means that I can draw the exact same picture for how this setup works and what Alex and Bob do, but now I interpret the things in the picture differently. Okay, so in quantum land, we can realize the twin state. So rather than as this correlated relation state, we can realize it using quantum entanglement. So there's a particular quantum entangled state called a Bell state, named after John Stuart Bell, which has a particular mathematical description in quantum theory and so on and so forth. But all you really need to know about it is it behaves just like a cup did before, and there's also a cap that goes with it. Okay, so we have a cup and a cap that we can put together and we can yank the wire. Now, a slight tweak we need to make from the crypto setting to the teleportation setting is there's not just one NOT gate involved, so we don't just have 2 outcomes, we have 4 outcomes. And that's because this measurement actually involves 3 different quantum NOT gates. Okay, so I can give you somewhat of an idea of why, or at least what these things are. If we go back to the qubit, remember that we chose to put the points at the North Pole and the South Pole as 0 and 1, as corresponding to the bit values of 0 and 1. And I also told you that the way that you can update qubits is by rotating the sphere. So one way I can do a NOT gate is I can just take this whole sphere and I can turn it upside down. Right? So that will send 0 to 1 and 1 to 0. But then, unlike with a classical bit, there's more than one way that I can turn the Earth upside down. I can turn the sphere upside down. And in fact, this particular measurement I do corresponds to 3 different ways I can do that. One is making a 180-degree turn around the x-axis. One is making that turn around the y-axis. And one is making that turn around the z-axis. Okay? And it turns out that this is a perfectly good quantum measurement that I can do. And also, a thing to note is that if I do a 180-degree turn, and then I do it again, it cancels itself out. So that behaves just like a NOT gate in that sense. Okay, so here was the crypto picture, right? And we explained what each of these things were. And the important thing was that whatever happens in this question mark here, be it just the do nothing or be it the not, as long as Bob does the same thing up here, then things cancel back out and Bob gets my bit. Okay, so let's change this from crypto to teleportation. And all we do is we change the thin wires to the thick wires to mean that this is now quantum states and processes. Okay, so here's my quantum state that I have in my lab now. Me and Bob share an entangled Bell state. And then I do something that is analogous to looking at my two bits together. I do a quantum measurement. And I get one of four outcomes. Either nothing or one of these three NOT gates. And then as long as Bob does the same thing here, it should cancel out. And, of course, it works. And the reason it works is for the exact same reason that it worked in the crypto setting. We just yank the wires, we cancel the NOT gates. And this is in fact how teleportation is done. I mean, I gave you this very simple explanation, and I didn't tell you, how I'm going to build this Bell state in the lab and so on. But this really is the trick behind quantum teleportation. So this is the thing that was described back in 1993 in this very fancy-sounding paper, teleporting an unknown quantum state via dual classical and Einstein-Podolsky-Rosen channels by Bennett et al. And this has even been used to teleport the states of quantum particles into space. So that's for just yanking the wire. I think this is a pretty impressive trick. Of course, that's not the only weird trick you can understand about quantum theory using these pictures. They also show us how to make quantum computers faster, how to optimize quantum computation, how to communicate securely using quantum crypto, how to calculate hard stuff like cracking RSA with quantum algorithms, and how to do very foundational things like prove that the universe is fundamentally non-local. There's a lot of weird tricks, and there's a lot of ways that you can show these things using pictures. So if you want to know more about any of that stuff, I suggest you pick up the book. It's pretty hefty, but it's got a lot of pictures, and if you have any questions, get in touch. I'm happy to help.